Chris Cole from Finisar. Ah, there we are. So it's been a while since we've done a presentation like this. A lot has changed in the market. Those of us who run large networks are familiar with the constant ebb and flow, and what we're trying to figure out is how do we get to 100 gig, what's beyond that point, but more importantly, when will we see the form factor and cost reductions that will make emerging technologies like 100 gig affordable for all of us? Chris?
Thank you very much. I'd like to thank NANOG for inviting me. It's a real pleasure to be here. You guys are our ultimate end customers, and so it's really your problems that we should be working on, and I look forward to learning more about what the directions are that we should follow. Here's an outline. I've organized it around data rates, starting out with 10G, which is prevalent today, moving on to 40, 100, and beyond 100. I've tried to capture from an optics perspective what the world looks like to us, which is 10G is the dominant interface today, and it's actually a very simple interface. I have a block diagram which shows a transmit flow and a receive flow. These optics are packaged in form factors called XFP and SFP+, which are differentiated by the type of electrical interface. So other than the size, that aspect is actually invisible to you. And it's very straightforward design. There's one path running at 10G, and on the optical side, it's one wavelength. And it's the same for both multimode and single mode fiber. They're duplex LC connectors, and other than the color of the fiber, it's very straightforward for you. However, that world is going to change. As we move up to higher speeds, things get more complex, and this kind of simplicity is actually going to somewhat go away. So as much as we'd like to make this a dump pipe to you, I think you're going to need to know a few more details to efficiently use optics. One topic I'd like to touch on is optics specifications. The optics engineer view of the world is in dB, or link budget. The major components of link budget are penalties plus loss. Penalties are what it takes to overcome propagating light through the fiber. So you may have heard terms like chromatic dispersion, which is different propagation of light at different colors, polarization dispersion. There's many other penalties. So these are things that we work on very hard, and it's essentially the price we pay to have a optical link. Loss is essentially what's useful to you. It's how much reach of fiber can we go across, how many connectors can we support. And so your view up to now has been strictly in meters. The dominant interfaces have been multimode, and that's really been sufficient to talk about optics strictly in terms of reach. Because for link budget, the penalties dominate, so reach is synonymous with penalties. But as we move into single mode interfaces, it turns out it's not sufficient just to talk about reach, because the link budget is mainly loss, and almost no one deploys the maximum reach. So even though the single mode interfaces you all use are 10 kilometers, there's very few links that are 10 kilometers. NANOG, in fact, supported the IEEE a number of years ago with a survey, and there's very few reaches above 5 kilometers. So reach is not synonymous with loss, and in actuality, what you care for single mode is actually the loss. So there's an example here. I'm not going to go through it for various reaches and what the losses are. You can use that as a reference. But the takeaway point is that for multimode, talking about reach is sufficient. But when you talk about single mode optics, you can't just talk about reach. You got to also talk about the dBs, because that tells you how many connectors you can go through, if you have passive splitter elements, etc. If you don't want to bother about dB and you have a guy in a three-piece suit with pointy shoes trying to sell you stuff, ask an optics friend. He's telling me 1 dB of loss is enough. Is that enough? Hopefully that will save you some grief in the past. I've had friends who operate networks get burned by this. We've helped them out, so if you have questions about it, ask me or ask someone you know in the industry. Why pluggable modules? That's the paradigm that almost the entire industry has adopted. Probably almost all the optical interface are pluggable module based. And now we're seeing some proposals in the industry to move away from that. So I want to give you a perspective why the industry has adopted. There's a number of good reasons. This is, by the way, from one of my favorite movies, The Good, the Bad, and the Ugly. So we have Clint Eastwood there on the right side, Il Buono. Pluggable modules means you can support multiple applications. You can plug in a multi-mode or single-mode optic. You can plug in a 10 or 40-kilometer optic all into the same port. It's pay-as-you-go, so you don't need to populate everything. If you get a failure, you can replace one link without affecting others. There's a common market and specialized R&D. The bad is it costs more because you have a separate interface. It impacts signal integrity, and possibly there's density limitations. And then the real ugly aspect of that is it concentrates the heat in the front end, so it makes thermal or cooling very difficult. But anyway, this is a good perspective as you may be facing choices to move to different paradigms. Let's move on to 40G. 40G multimode, the IEEE standard, is actually a departure from the 10G standard because it moves to parallel fiber. So instead of a duplex LC, you now have an MPO connector. There's some details there for how the connector is structured. You can have a parallel module like a QSFP, but now you have to deal with ribbon or parallel fiber. So even though the per lane rate is still 10G, the way we achieve the 40G rate is running 4 parallel fibers in parallel. If you look at 40G single mode, from your perspective, nothing's changed because you're still only dealing with a duplex LC connector and duplex single mode, but in fact, that fiber is now carrying 4 wavelengths. Again, for those interested, there's a graph showing you the wavelengths below. This has been used in transport and long-haul networks for a long time, but it's the first time that it's going to be deployed widely in a data center. So in this case, actually, the added complexity makes your life easier because you maintain the duplex LC paradigm. Another new development which will affect your life greatly is high density through breakout connectors. This is an example of a cable for a QSFP 10G breakout. So you would have 4 10G channels in one QSFP with an MPO connector. So at the top you have the MP connection, but then you break it out into 4 separate duplex LC pairs. So from an operational standpoint, you now have to worry about things called octopus cables, which are MPO on one end, duplex LC on the other, and you have to start worrying about how those MPO connectors break out. Why are we doing that? Why are we imposing this complexity on you? Because the density advantage is enormous. On the first line there, I've listed what you can achieve with an SFP+. You can get 48 ports in a 1 UI card, and that's considered state-of-the-art for 10G. If you go to a QSFP with 4x10G octopus cable, you can increase the number of 10G ports to 176. And if you go to a CFP4 with 25 GIO, again in a double density configuration, you can get 360 10 gig ports in 1 UI card. So that's the number of ports you can almost get in a half rack. So the payoff is enormous, but the complexity of network or data center operation goes up. And then I've listed some powers. So the power's going up with the number of ports, not proportionally, so we're able to keep the per link power down. But unfortunately, the total power is increasing, so your thermal management is going to increase. Very large data centers actually use their cooling as a strategic advantage. You've probably seen some photos of Google data centers now. They make a huge investment in thermal, and that's something you should really be planning on. If you intend to increase the density, the interconnect in your network, you got to start thinking about advanced cooling. Moving on to 100G, here's a progression of 100G modules. CFP was the first generation form factor. CFP2, which is twice the density or half the width, is being introduced now. CFP4 will be coming along in a few years. And there's also an upgrade of the QSFP form factor to 100G operation. What that buys you is the top UI card shows 4 CFPs. So that's a maximum of 400 gig that you can get on a line card. Actually, first generation systems either only had 1 or 2 ports, typically on high-end routers. CFP2 will enable 8 or 10 ports, so that's a terabit. CFP4 can go up to 16 ports, and in a double density, you can get up to 3.6 terabits. Again, looking at the 100G generations, another form factor that some of you may have encountered is called CXP. That's a multi-mode only form factor, and it's based on a 10 by 10 configuration. So this can be used either for SR10, which is parallel single mode, so again, using 10 instead of 4 fibers in parallel to carry 100 gig, or you can actually use it to have 10 gig SR ports. Very high density configuration. The first generation 100G single mode was what's called CFP form factor. By the way, it's about the size of a mobile phone. It had a 10 gig IO electrical interface, but used 4 25G wavelengths. Again, the WDM complexity is actually making the interface simpler for you as an operator because you're only dealing with a duplex LC connector. Second generation, which is being introduced right now, and the IEEE is actually just completing standardizing second generation 100G. One is called, for multi-mode, the standard is SR4. So it's very similar to the 40G standard in multi-mode that's being deployed, which is 4 parallel fibers carrying 25G wavelength. So you could actually, if you deploy 40 gig SR4 multi-mode, you could actually reuse that infrastructure for 100 gig SR4. They're both specified for 100 meters. I'm showing a CFP2 form factor, and again, other form factors like CFP4 and QSFP28, which have twice the density, will also become available next year. For single mode, duplex LC, pretty much an interoperable interface with Gen 1. You can connect Gen 1 to Gen 2 to Gen 3. The changes are essentially invisible to you because it's lower cost, lower power technology, more highly integrated, with higher speed electrical I/O. And again, the density goes up. What are some technologies that are on the horizon for us? One thing is the rate is going to continue increasing. So 40 gigabits per lane. Remember, the 40G high volume interfaces are 4 lanes of 10G, whether that's fiber or wavelengths, they're 10G wavelengths. We're now looking at 40 gigabits per lane, which is referred to as serial, or 1 by 40 architecture. Why is that important? It's important because it's going to make optics very cheap at the 40G rate. Frankly, my objective is to kill copper with this architecture. I'd like to see all the server to top of rack interfaces at 40G be optics. We didn't accomplish that at 10G, shame on us. If we can't do it at 40G, I think the whole industry should be fired and need some new young guys to do it because we have physics on our side here. But anyway, that could be very exciting to have basically no more wires in the data center. 50 gig, again, increasing per lane, can double 100G density by going to a 2 by 50G architecture versus 4 by 25. A huge debate in the optics industry is parallel single mode. So this is similar to the parallel multi-mode SR4, but it's parallel single mode. Now, parallel multi-mode, if you just run through the numbers, makes sense from a cost perspective for 100 meters or less. But the debate is whether parallel single mode is actually interesting in the data center for longer reaches. If you're going 500 meters or 1 kilometer, is it okay for you to have anything other than duplex single mode? And in the Q&A, if there's a little bit of time, I'm actually going to ask maybe for audience reaction if the moderator allows me. But very, very big debate in the IEEE. The other major shift is board-mounted optical engines, so actually moving away from the pluggable module paradigm and then higher order modulation. And I'll go into the last two in a little bit more detail. So this is a photo of a line card. The area in the center is area for a system chip like a switch ASIC, so let's say a MAC ASIC that routes IP traffic. And then it's surrounded, what you're really seeing there, heat sink, but there are optical engines or optical devices that are directly mounted on the board below those heat sinks, and they surround the ASIC. And then fiber is taken out off of them, either on the board or as direct fiber. The big advantage of that is that you can mount these optics two-dimensionally on the line card, so potentially more of them, and then the electrical connection to the optics from the ASIC is very short. The disadvantage is that now you've tied up the whole card with one type of optics. So here's an example from a router company called Arista that's just been recently introduced, where they've put optical engines on their card right next to the ASIC, and all they have on the front panel are dedicated MPO connectors. So there's 3 banks of 4 connectors which can be configured either as a 100G port, 3 40G ports, or 12 10G ports. But in this case, it only supports multi-mode. So if you want to have some of those ports support single mode, you don't have the option of replacing that. So it'll be very interesting to see how you guys like this kind of a paradigm shift. And again, I'll ask during the Q&A if you have any thoughts on this. Moving on, higher order modulation. This may sound pretty esoteric to you. I'll tell you why it's important to you a little bit later. Let me explain what it is. So up to now, the rate at which we could send data over fiber for data center applications has been a product of 3 parameters. The symbol rate, or how quickly we turn the light on and off, the number of fibers, and the number of wavelengths. And you multiply those out, and that gives you the data rate. So the new kid on the block is number of bits per symbol. So traditionally, it's been 1 bit per symbol. But now, just like in the transport network, or just like in any other area of communication, like wireless, wireline, whether it's DSL or even voice-based modems, all of those standards have more than 1 bit per symbol. And finally, optics in the data center is catching up to that. We've not been using it because it's expensive and complex. So we've been able to get away just cranking the knob up on the speed, but we're finally reaching a limit of that. I have an example of 2-level, which is the traditional optic signaling called PAM2 or NRZ. It's the I on the right side. 1 is encoded with light on, and 0 is encoded with light off. And PAM4 actually has 4 levels. So 2 bits at a time are encoded. So this is probably the simplest example of higher order modulation. There are many more complex examples like phase, frequency, and subcarrier modulation. But that allows you to reduce either the speed with which you're switching the light, or the number of fibers, or the number of wavelengths. Now, you might ask, why is that interesting to me at all? It's just the problem you guys have. As we do all these things, these optical interfaces are going to become incompatible with each other. For example, the 40G, the parallel fiber, that's really not compatible with duplex fiber. As you have higher order modulation, they potentially won't be able to talk to the simpler modulation formats. We're going to try to work as much as we can to make that invisible to you. But I think you'll see that you have to manage somewhat more optical skews than you had in the past, just because people are unwilling to pay the cost of the most sophisticated skew for their lowest cost applications. What's next? The next speed is 400 gig. That just got approved by the IEEE. The first meeting of the IEEE was in Victoria, British Columbia, where we started to talk about how we're going to do 400G. By the way, I highly recommend, if you've never been to Victoria, please go. There's a beautiful island. The kayaking is wonderful. So if you're into outdoors, make it a point to get up there. First generation optics, both multi-mode and single mode, there's a very strong consensus in the industry that the initial volumes are going to be low, and we don't want to invest a whole lot of money on it to sell a few hundred interfaces. So for multi-mode, we're actually looking at 16 parallel fiber lanes, 16 by 25. So that will reuse the multi-mode standard we're just completing for 100G. I'm showing you a new connector, which is 2 by 16. MPO, all these parallel fiber connectors that you use to run bulk links across the data center have been by 12. The by 12 is a historical artifact from when people would efficiently pack copper cables. It's sort of like stacking oranges. But we're trying to move to by 16. So this connector was developed by US Connect, and you'll see that for 400G. Facebook now has this Open Compute initiative. They worked on a parallel connector with Corning. That's a 4 by 16 connector, so you'll see the by 16 more frequently now. Here's a diagram I borrowed from my friends at Juniper. It actually shows you how you'll be able to get a 400G link just by combining the output of 4 100G modules, again, using an octopus cable, this time in exactly the reverse way as you do for multi-link modules. Here you take 4 links and you combine them into a single by 16 MPO link. So you can actually then have a card where you either have N by 4 times 100G ports or N by 400G ports. For Gen 1 400G single mode, we're proposing to use 400G links. So again, you won't have duplex LC to carry 400G, but you'd actually combine, just like for multi-mode, 400G links in a parallel cable. Long term, for single mode, we certainly want to return you back to a duplex LC paradigm. Here I'm showing 8 by 50G wavelengths. You could actually have 4 wavelengths with higher order modulation. So hopefully, again, we'll make all of that complexity invisible to you so that when 400G hits your data centers in volume, it's going to be duplex single mode. So what's after 400G? 1 terabit's been discussed a lot. Lots been published on it. Part of picking 1 terabit is it's a vestige of Ethernet going up in 10x jumps. Any way you look at a terabit, it's going to require a lot of R&D investment, and a 2.5 speed increase from 400G is just not compelling for that. So my prediction is that the next Ethernet speed will be 1.6 terabits. 4x speed increase feels reasonable for a large R&D investment, and I feel it's actually more likely to be representative of future speed jumps. So the 10x speed increases, I don't think we'll see those anymore. And this is much more similar to the transport speed jumps. They used to go up in 4x increments because they were, in essence, leading the technology. Ethernet speeds always lag transport. That's no longer true at 100G. The two aligned. And so I think what we'll find is 4x increments going forward, just because this stuff is hard. It's not easy to make a 10x increment. Gen 1 1.6 terabit Ethernet is likely to use the same paradigm of 400 gig interfaces, which hopefully will be mature at that point. So in summary, 10G was very simple. There was actually not a lot of complexity, either duplex LC multi-mode or single mode with pluggable transceivers. At 40 and 100G, we're seeing more complexity now. Parallel fibers for multi-mode, WDM for single mode, big change for you will be multi-link modules with breakout cables, and then board-mounted optics. We'll see how that plays out. It's a departure from the pluggable module paradigm. It'll be very interesting how well you guys like that. Future 400, 400G, and 1.6 terabit technology will do what we've always done, which is we'll crank up the speed knob. We'll be looking at parallel single mode as well, and higher order modulation. And then there's a lot of signal processing that's behind it that hopefully will hide this complexity from you. Thank you very much.
We have a few minutes for questions. All right.
Can he be disqualified from asking questions?
No. Ted Seeley from Sprint. Hey, Chris, go back to your slide where you had 40 gig serial on there. I think it was in your futures looking forward one. I noticed you had 40 up there, but you don't have 100, and I want to know why. You got 50, but no 100. And if I'm not mistaken, your 40 gig serial prediction, right, is 2 years earlier than everybody said it was going to happen. So why no 100?
Well, so first of all, just to put some dates on it, we've started a project in the optical interface to adopt 40G serial electrical interfaces. And in that project proposal, which I wrote and published last year, we projected the very early deployment in 2016 and volume deployment start in 2017. And I continue to stand by that projection. So I don't think it's too much earlier than anyone else. It's aligned with the fiber channel roadmap as well as several other ASIC roadmaps. So I don't think that projection's out of line. I should have clarified, this is 40G serial NRZ. So it's dirt simple, simplest kind of NRZ, which you really need to have if you want to compete with copper. I do have 100G serial here implicitly, which is 50 gigabit or gigabaud per lane rates. So for example, 100G serial with higher order modulation has been proposed in the IEEE. Most of the industry feels it's too early, but you will see 100G per wavelength or per lane at some point, both electrical and optical, but I think it'll be about 3 years later. So the deployment of 100G serial electrical, my guess is 2020 maybe, 2021.
Okay.
Did that answer your question?
It did, and,
Yeah.
and thank you.
Okay.
Good talk.
And thank you for the question, Ted.
Will?
Hi, Will Hargrave from LonApp. Thanks for the presentation. You asked some feedback on how we felt about multi-way 10 gig on, say, four pairs of fiber.
But multi-fiber, yeah,
multi-fiber.
parallel fiber.
Yeah. So broadly, in the kind of colo market, we're paying per pair for fiber. So a standard that requires us to use lots of pairs means that it just scales our costs like linearly. So it's not really compelling for certainly for people who are operating networks in colo facilities. If you own the infrastructure, then obviously it's a different sort of thing. But the cost is all in the actual. If you install like a bulk cable in a facility, the cost is all in the termination. The per splice cost. The actual cable is not very much.
Okay.
So just my perspective. And multi-mode, I have very little interest in using that. It's fine, again, in your own facility or within your own suite. And a lot of people just view like the MPO connectors as a kind of, not quite a proprietary, but like a specific purpose interconnect, and don't really have much interest in interfacing that to bulk fiber cables that leave the facility.
Okay. Thank you very much.
Thanks.
Phil Rosenthal from IS Prime. So also some feedback from my perspective. I agree, multi-mode, not at all interesting to me. I want single mode, and for me, long range, 40 kilometer, 70 kilometer, maybe 100 if you could do that. Also, colored optics are very important for us now. So even if you cannot do, serial, 40 gig waves, if you could do like say, this fits into DWDM channels 16, 17, 18, and 19 for 40 gig, that would be excellent for us. But as it is right now, I agree. I'm not going to order 4 pairs of dark fiber to go between buildings for one circuit. The possibility of outage actually goes up because, there can be a partial fiber cut in.
What about within a building? Would you deploy parallel single mode within a building?
Within a building, maybe, but, typically for us, within a building, our traffic requirements aren't, it's not that large because everything is feeding towards an aggregation point, and then from that aggregation point, that's when it leaves the building at higher speeds. So within the building, even gig E is still plenty for us. Leaving the building, 40 gig would be very useful, so.
Okay, that's very helpful. Thank you.
Brian Dixon, VeriSign Labs. Question about the single mode doing WDM instead of parallel fibers. How feasible would you see that for this
This is
specific?
for which interface?
For pretty much any interface.
So again, as you saw in my presentation, both the 40G and 100G standards are duplex single mode, and they're WDM, but they're more expensive. Now, we're driving the cost of that down, and you'll actually, in 40 gig, it's actually quite cost effective. 100G is rapidly falling, but it's still not at a price point that's interesting. And so people have proposed parallel single mode as an interim solution to use lower cost non-colored optics, basically running over parallel single mode fiber. And there's a big debate about, is this really a solution of interest to end users, or should we really focus on driving down the cost of the colored or higher order modulation optics? That's the debate.
I think the colored is definitely worth investing in. I think there's some other interesting design methods like the onboard optics. If you do that with colors, then when you're doing stuff with lanes, you can actually configure some number of lanes per physical interconnect interface based on the colors.
Sure, now that's yet another level of complexity, which is you're now switching colors, which I didn't touch on, but that's essentially sort of a mini transport network in the data center. All the colored stuff I discussed is point to point, so you don't treat the different wavelengths differently. But yes, I understand what you're asking for, and that's in the future as well.
Right. So what I was getting at is instead of limiting yourself to fixed numbers of n, you can do variable numbers of n by having onboard mirrors or something like that.
So we could do that today. Would you be willing to pay the transport optics cost in the data center for that?
You should have one fixed cost for the board. It shouldn't matter
No,
beyond
no,
that.
but the optics will be very expensive. That's the rub.
If you already have to go there, you may as well.
Okay, thank you very much. Would the chair indulge me take a quick straw poll, or are we out of time?
You can take your quick straw poll. Ted, I got to ask.
I'll ask them, sir.
Thank you, because we're 5 minutes over, but do your quick
I'd
poll.
like just a very quick yes/no question. Would you use parallel single mode or consider using parallel single mode in your data center? That will be response A, and response B, you really won't consider it. So who would not object to running multiple strands of single mode to carry one link? Who would object to actually deploying parallel single mode on a large scale? Okay. All right, so it was about 4-1 with 3/4 not responding. Would you say that?
That's about right for this crowd.
All right, okay. Well, thank you again, and please, I'll be at the social. I really want to know what your problems are. Please come up, say hi, and tell me what problems you'd like to solve, so we're working on the right things.
Thank you very much, Chris. We're going to go into a break. We have two tracks after this. Best current operations practices, which is in here, and the security track, which is in Salon 3. Just of note, the survey prize that we were talking about earlier is an iPad mini. So please fill out your surveys. Thanks.